guys, welcome to Kinematics Packet 10. This problem example is one that I'd like you to save and refer back to it pretty often because you are going to be seeing different types of problems now. We are moving on from one-dimensional kinematics, meaning that the object or the motion that we're looking at is going in either the horizontal, the X, or the vertical, or the Y. And now the objects are going to be going in both of these directions at the same time. What's important to remember is that when the objects go in both directions at the same time, the vertical motion is independent of the horizontal motion, and the horizontal motion is independent of the vertical motion. And that's a very difficult concept to put your brain onto, because it just doesn't seem like it would be that way. It's going to be a little more challenging, but we know that if I throw a ball harder, it doesn't mean that gravity affects it less. If I hardly push something off the table, or if I give it a big shove off the table, it's going to be falling independently of that horizontal push I gave it off the table, or whatever caused the horizontal motion off the table. So it's just some pointers that I'd like to bring to your attention. Grading your last test, you are using delta x whenever you please. We can no longer do that. Delta x is only to be used for horizontal motion. Delta y can only be used for vertical motion. This is very important because it's going to cause you to make silly mistakes that you will not know what you did wrong. Acceleration due to gravity can only happen in the y direction. If I throw something horizontal to the ground, that has nothing to do with acceleration due to gravity. In these problems, there will not be acceleration in the horizontal direction, and horizontal direction is going to be constant velocity. For purposes of this course, this year, horizontal motion in projectile motion is constant velocity. So in our sample problem, a ball rolls off a 0.7 meter tall table with an initial velocity of 1.3 meters per second horizontal. Where does the ball land, and what is the final velocity of the ball? So there are two parts to this problem. First, we're going to solve A, and then we're going to have to go back with our new knowledge that we did from solving A, and we're going to solve B. So all physics problems start with the picture. So this picture shows what we know. The table is 0.7 meters tall. The initial velocity, the only initial velocity we have is horizontally, and it's going 1.3 meters per second. We know that our final velocity is going to be have components of both the y direction, the vertical, and the x direction, the horizontal. So that means we're going to have to use Pythagorean theorem and some of our trigonometry to solve this final velocity. It's no longer going to be a simple positive or negative. The second thing we do is make a list of what we know. So our data table is now going to be 10 items. There's going to be an x column up and down and a y column up and down. Going across, we're going to have our displacement. So notice that delta x and delta y are in the same row. Vxi and Vyi, our initial velocities, are on the same row. Vxf and Vyf are on the same row. See the organization, accelerations are on the same row. And our delta t's are on the same row. Because time unites the problem, they get an equal sign. So if I can find time on one part of the problem, I can use that time for this other part of the problem. Only time unites the problem, but it's very helpful for what we'd like to do. So when you're writing your data table, I'd like you to keep yours showing the same type of organization. You should be filling in numbers so that it makes it easier for you to use the data table, because it's a tool in solving a problem that we're going to need to use. So step 3, we're going to select an appropriate equation. The question asks you, where does the ball land? That means, what is delta x? The solution equation must therefore include a delta x. So when we look through our equations, we've got 4 of them. The one that we would choose is delta x equals Vx delta t, because we know that the velocity in the horizontal is not changing. So that's the easiest equation for us to use. But we have a problem. we don't know delta t. We know our Vx, but we've got two equations and we have two unknowns. So we need another equation to use, and we're going to have to think about what we're going to do. So we know that that there is no acceleration in the horizontal. We know that we need a delta t to get our v, to find our delta x. And we also know that delta t is on the x side is equal to delta t on the y side. That's very helpful. In these dropped ball types of equations, we can use delta y equals vyi delta t plus 1/2 ay delta t squared to solve for delta t. This is actually pretty nice because vyi equals 0 because the ball rolled off the table. It had absolutely no vertical motion when it started. It had horizontal motion, but it didn't have vertical motion. So it's going to make it nice and easy for us to solve because vy delta t goes to 0. So when we solve for this equation, delta t equals the square root of delta y divided by 1/2 a. Delta t equals 0.38 seconds. So I'm going to take that 0.38 seconds, which I figured out on the y side, and I'm going to put it onto the x side, because time unites the problem. So delta t equals 0.38 seconds. I plug that in. I find my delta x to be 0.49 meters. Okay, that's part A done. Good job. Now I have to go back and solve for part B. So I'm going to revisit my picture. And my picture, point over to the right, and I've highlighted for you the final velocity, what I'm going to have to find. I already have a Vxf because it's equal to the Vxi, but I do not know Vyf. When I find Vyf, we can use Pythagorean to find that Vf, the final velocity. So I updated my data table. I plugged in that time is going to equal to 0.38 seconds. I plugged in delta x equals 0.49 meters. So now I'm going to be looking for Vyf. I can do that pretty easily by using kinematics. Vyf is the second equation on the paper. Vyf equals Vyi plus ay delta t. So my Vyi goes to 0. So when I go ahead and solve for this, I find that my final velocity is going in the y direction, is going to be negative because it's going down, and is equal to negative 3.7 meters per second. So now I have to find my final velocity. So I use Pythagorean. I square my x velocity, I square my y velocity. I know it's going downward. When I take the square root, I take the negative. But because velocity is going to be something where I have to have a direction, I need to do a little more work. So we have to remember what we did earlier in the year, and we're going to be using tan to the negative 1 to find our theta. So first I have to find that it's opposite over adjacent. So I find that tan theta is going to equal to negative 2.18. And then I can plug that into theta equals tan to the negative 1, negative 2.18, and I end up with negative 65.36 degrees. So if I get a negative degrees, I know that I have to be in either the second or the fourth quadrant. If it were positive, it would be in the first or the third. So I know that my x direction is positive, or my horizontal is positive, and I know that my vertical direction is negative. So that means I have to be in quadrant 4. And the picture that we had earlier, going back to the picture definitely verifies that I've got negative y velocity, positive x velocity, so I have to be in the fourth quadrant. So because I'm in quadrant 4, I have 360 degrees, take away 65.36 degrees. I'm going to end up with 294.64 degrees. So my final answer is that this ball is going 3.92 meters per second at 294.64 degrees. So hopefully you found this interesting, helpful, and everything else. You may refer back to this video many times so that it can be helpful for you learning how to do these types of problems. Thank you for tuning in. I hope you tune in quite a few more times.